Howdy, howdy. This is Mr. Potter. In our previous lessons, we've come up with quite a few ways to find the derivative function, or the instantaneous rate of change function for given situations. So one of the things I want to talk about in today's lesson is why are we doing this? In other words, what are the real purposes, the real uses, real life uses of derivatives? And so one of the things I want to talk about is this instantaneous rate of change that we've been discussing. So let's say that S of t represents the distance or displacement. Then an object takes place. In other words, S of t is going to represent how far away from my starting position, or the distance that I have traveled. If this is true, then if I'm looking at S prime of t, this of course is the instantaneous rate of change of distance. So if my distance is changing, this is velocity. So the instantaneous rate of change, one of the representations that we've talked about, is that it's the velocity at a particular time t. So we could call this v of t. And one of the things about velocity is that it usually has a sign that indicates if I'm going forward or I'm going backwards. But if I'm going backwards 30 miles an hour in a car, I'm going 30 miles an hour in a car. And we usually talk about that from a different quantity, a quantity that we call speed. And when I'm talking about the speed of something, I'm usually not indicating a direction. I'm not usually indicating whether or not I'm going 30 miles an hour forward or 30 miles an hour backwards. I just happen to be going 30 miles an hour. And so that means, because we have the absence of sign, this really is the absolute value of my velocity function, or the absolute value of my instantaneous rate of change function. So speed is going to be the absolute value of my derivative function. And the other thing that we talk about when we're talking about position, remember we discussed how velocity changes as well. Velocity is a function, and this function is experiencing change as well. So I can talk about the rate of change of velocity, my v prime of t. And we usually call this change in velocity acceleration. so we usually give that the a of t designation. But remember that this velocity function that we're talking about, this is really the derivative of my displacement's derivative. So this is really the second derivative of displacement. And so we have all of these relationships for the instantaneous rate of change for a practical situation where I'm falling. So let's say that the height above the ground for a particular object, say me, is negative 16t squared plus 20t plus 8. And we're going to go through several problems with this particular scenario. So the first question I have is, what function describes the velocity? So remember that velocity is the rate of change of this height. So this would really be h prime of t. So when I take the derivative, I'm going to be getting negative 32t plus 20. And because it's a change in position, a change in distance, if this function represents feet above the ground, then my velocity would be in terms of feet per second. So I have a function that's based on the velocity of my situation. And of course, what's happening here is if I were to graph this function, I have a y-intercept at 20, and of course that represents my velocity when t equals 0. And my velocity is going to come down at a slope of negative 32. That really is the rate of change of my velocity. That number has a very special meaning, which we'll talk to in just a few minutes. But several things are happening here. One, I'm going to have a positive velocity because this y-axis is representing my velocity until some point, and then I'm going to have a negative velocity. But if I'm looking at this from a speed standpoint, my speed is going to be decreasing, and then my speed will be increasing. Now increasing in the negative dimension, mind you, but I'm still going to be going faster and faster. It just happens to be down. My speed is the absolute value of my velocity. So it's going to be the absolute value of this derivative, negative 32t plus 20. And of course, I know the absolute value parent function tends to be a v. This just happens to be translated over and a little bit steeper. So I actually have something like this on my scale for t and speed. So my speed is going to be slowing, 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 slowing to a particular point, and then I'm going to be increasing speed as I start to fall down. Now, a better picture of what's going on is this pink graph, where my velocity started off at 20, which means I'm going up 20 feet per second. I reached a place where I was going up 0 feet per second, kind of acting Wile E. Coyote, and then I start falling at a particular rate. But the speed that I'm experiencing, I have a speed, but I'm slowing down until a certain point where my velocity is 0. And then I start speeding up as I fall towards the earth. Now, if I ask the question about acceleration, remember that acceleration is the second derivative of this function, which is going to be the derivative of my derivative. So I want to take the derivative of the negative 32t plus 20. And of course, the derivative of this function is just negative 32t. Negative 32. And this is a rate of change of a rate of change. So that means that my position is dropping 32 feet per second each second. And physicists will like to write this as 32 feet per second squared. So I'm falling 32 feet per second squared, even though what's happening is my velocity is changing by a certain speed each second. So that's what acceleration is. And for those of y'all who've done a little bit of physics, this negative 32 is my acceleration constant when I'm dealing with English units. 32 feet per second each second. Now, many of y'all are probably more familiar with the negative 9.8 meters per second each second. But of course, these are the same. The only difference here is the relationship between meters and feet. The fact that there's about 3.2 meters, I mean 3.2 feet for every meter. So we can do some interesting things with this. For example, let's say that I want to know when is my velocity 0. So if I take a look at my velocity equation, which is the derivative, negative 32t plus 20, and I want to know when this is equal to 0, solving for this, I find out that t ends up being 5/8 of a second. That means that my velocity is 0 after 5/8 of a second of this motion. And remember that what's happening is my velocity starts off positive. My velocity started off at 20. And then my velocity eventually became 0. And then my velocity eventually became negative. So what's happening is I'm going upwards, and I reach a place where my velocity is 0. The slope of this tangent line is 0. And then I start falling. So this is what's happening to my height as t changes. And this idea where the velocity is 0, velocity is my instantaneous rate of change. It's also the slope of my tangent line. And if I have a horizontal tangent, that usually means that I have some type of maximum or some type of minimum, because that's where humps are, where I have horizontal tangents. And we'll talk more about that in chapter 4. My initial velocity is what I get when I set t equal to 0. So in other words, what is my velocity at t equals 0? So I'm going to have that same derivative, negative 32t plus 20. So that's the 20 feet per second that we were referring to. So I can, from all of this information, I can find out stuff about what's happening to me as they travel along this parabolic path, going up until I reach a certain point, and then coming down due to gravity. So a couple of more things I can do here. So I can ask when is my velocity? Four feet per second. In other words, when am I going up at 4 feet per second? I start off by going up at 20 feet per second. I eventually hit 0 feet per second, so there's got to be some place in between by the intermediate value theorem, where my velocity is 4 feet per second. In other words, where negative 32t plus 20 equals 4. And so if I solve this equation, I find out that t ends up being 1/2 of a second. So after 1/2 of a second, my velocity is going to be 4 feet per second. A different way I can ask this question is, when will my speed be 4 feet per second? And this is a slightly different question, because remember, my speed doesn't really care about the sign. I'm really using my speed function, which we said was the absolute value of my velocity function, or the absolute value of negative 32t plus 20. So I really want to know when this equals 4. And so if this is true, that means I've got two situations. One situation, which we just did, setting the velocity equal to 4. But another situation where I set my velocity equal to a negative 4. And so I really have two different questions, two different equations to solve. This is the solution that we just did, where t equals 1/2 of a second. But in this situation, when I solve, I have negative 32t equals negative 24. And so t ends up being 3/4 of a second. And this actually brings up an interesting point. If I look at my graph at t equals 1/2 of a second, my velocity is 4. I'm going up to a slope of 4. And at 3/4 of a second, at this point, I'm going down with a velocity of 4, negative 4 feet per second. But I still have a speed of 4. And because this is a parabola, my vertex is exactly halfway between this, which is the 5/8 of a second that we had before. That's the place where my velocity was 0. So there's a lot of really good ways that I can ask questions or answer questions, real life practical questions, using the derivative. So I want to talk about some different situations. So let's say I'm talking about the area of a circle. The area of a circle we normally write from geometry as pi r squared, but my area of a circle is a function that depends on the radius. So this is really pi times my radius squared to find the area dependent on the radius. And my units here are going to be square inches, or square miles, or square some distant unit. If I'm looking for the rate of change, the derivative of r, this is how much my area is changing each inch, or the area is changing each foot. And the derivative of this is 2 pi r. And this is rather interesting because, one, my units are going to be inch squared per inch, and it looks like this should eliminate down to just 2 pi r inches. But it's also interesting in that if I have a circle, 2 pi r describes my circumference. And so when my area increases, it's going to increase at that circumference boundary. It's going to increase where the circumference is, because it's going to increase equally in all directions. And of course, my circumference is given by the formula 2 pi r. If I take a look at this from the standpoint of the volume of a cube, I know the formula for the volume of a cube depends on the length of the side. It's the side cubed. And of course, my units here would be cubic inches. But if I look at the rate of change of volume, the derivative of this would be 3s squared. And because I'm talking about the rate of change, this is inches cubed per inch. Now this looks a lot like inches squared. And I do have something that depends on the side square. What's really interesting is if I were to draw a cube, the thing is, when I increase the increase of volume is going to be increasing this way. It's going to be increasing this way. And it's going to be increasing this way. In other words, the increase in volume is going to come from each of the three faces of my cube. And so I find out that the change in volume, it's not equal to my surface area, but I really could think of this back corner here being a fixed point and expanding in the three x, y, and z axes direction. So it's proportional to my surface area. And this is an interesting relationship we'll address more in chapter 4 after we've learned some more derivative techniques. But there is one more real-world practical application, and that's dealing with revenue. So let's say that I'm trying to sell a product, and the amount of money that I get for selling my product can be described by this function. R of x equals x cubed minus 6x squared plus 12x minus 90,000. And of course, it makes sense that my revenue should be dependent on the amount that's a fixed cost. Like this is the rent for my factory, or this is the salary that I have to pay every month. But as I produce more products, I do expect the amount of revenue that I take in to get bigger. So what's happening is x is the number of products and R of x is the amount of money that I'm getting in dollars. And so what I want to do is I want to look at this rate of change. So if I look at the rate of change, R prime of x, my units are going to be dollars per item. In other words, this is how much my revenue is going to be increasing or decreasing based on each new item that I sell. So the derivative here is 3x squared minus 12x plus 12. And notice that the change in revenue that I get has no bearing on how much of the salary or the rent or the other fixed costs of running the business. It only depends on these terms where the number of items that I'm selling directly changes. Whether I'm adding because I'm selling more items, or I'm subtracting because it takes more raw materials to create more items. I'm given this function, and this function has a cost in terms of dollars per item. And there's a couple of ways to look at this. One is at x equals 10, the amount of change of revenue is described by 3 times 10 squared minus 12 times 10 plus 12, or 300 minus 120 plus 12, or $192 per item. And so that means that this situation, every time that I sell an additional item on top of the 10th item, I should expect to have an increase of about $192 in revenue per item. Now, obviously, if I'm selling an 11th item, I'd want to figure out what happens to R prime at 11. And of course, that will change. I'll either be increasing or decreasing because this derivative is a rate, but it is a function that has a change as well. Something that's even further interesting is if I set this R prime equal to 0, then I'm describing a situation where I have a horizontal tangent, which means either I have a plateau where my revenue was increasing and now decreasing, or I have a dip where my revenue was decreasing and now increasing, or I have a situation like this where I do have a horizontal tangent line, but my revenue could be a constant increase, or it could also be a constant decreasing here. So it is something to look at, this what we call marginal revenue, which is found by taking the derivative of my revenue function. Businesses will often use this to look also at marginal cost, to look at the cost change per item. Because if I've got a situation like this, I'm going to want to find wherever my minimum costs are. Ideally, I'd want a situation like this where there's a certain number of products I can make that would minimize my cost. So there are a lot of real-world practical applications for derivatives. And it's important to realize that that's one of the major uses of derivatives is to try and use these things in the real world to describe motion, to describe volume, or to describe what's happening economically, either to my revenue or to my cost. So, this is Mr. Potter. Thank you for watching. Have a great day.